We are now going to talk about raw materials for petrochemical industries. We will talk about natural gas and other gases and also other sources, not only other gas sources. So let's start. So first, the main feedstock for any petrochemical industry will be natural gas and crude oil. But actually, this is not the only sources. There is other feedstock or sources for the petrochemical industry. For example, for the gas sources, if we are talking about gases, we can find natural gas, which is a normal thing that we know. We have refinery gas, we have shell gas, we have gas hydrates, cool with methane, and cool actually biogas and geopressurized gas. In this lecture, we will talk briefly about each one of these gases, how we produce these gases, and we will focus mainly on natural gas production and the cleaning of this natural gas. Also, there is other sources from oil, which is the known crude oil. Other sources like oil shale and shale oil, light oil, tar sand, and coal again. Okay. So also we will talk briefly about each one of these sources and what is the composition of these sources. Why we would like to know the different sources of for the petrochemical, because actually we want the building block, we want to reach to the building block or produce the building block for the petrochemical industry. The building block for any petrochemical industry, as we will see here in this graph, is methane, ethylene, propylene, butane, butylene, butadiene, and PTX, which is aromatic base, benzene, toluene, and xylene. So this is the building block from which the other intermediate or the other final product of the petrochemical industry will be produced, like the polyethylene terephthalate, polyvinyl alcohol, and the other any other polymers or any other end product will be based on one of this building block. Okay, as you can see here in this photo. I like this poster. Okay. So the starting point to produce any of these building blocks will be either crude oil, natural gas, and coal, which is the main known sources. But there is other sources also we will talk about in this lecture. So let's start first with the natural gas. So this is, will be just to know this is will be the main focus. Like we will be talking about natural gas for 30 minutes or so, how to produce this natural gas, how to clean this natural, not produce, how to clean this natural gas and reach to the purity that is required for the petrochemical industry. So actually, natural gas it has two types: the associated gas and non-associated gas. So associated gas in the reservoir, you know that natural gas can be co-produced with crude oil. So reservoir can contain crude oil and natural gas, and also there can be some reservoir with only natural gas alone, which is the non-associated natural gas type. Natural gas is not only the main component in the natural gas is the methane, but there is other gases coming out of with the natural gas with the methane, like the ethane, propane, butane, up to C7. We can say that up to C7 will be heptane. Okay, so if this is not non-associated. Okay, so if we look at the natural gas, of course, the composition of the natural gas differentiates with the change in the field. So not every field has the same composition of natural gas. There is different composition according to the field that is produced. Okay, so as you can see, and also if this is non-associated gas, there is different. It is different than if it is associated gas. So, for example, as you can see here in this table, we have non-associated gas type and associated gas type. Actually, the most known is the non-associated gas type are mainly methane. So the composition of methane is higher in the non-associated gas type. So this is general rule. Okay, so for if we see look at the non-associated gas, we will have methane here, the composition which is 95%, and then we have ethane, we have propane. Okay, We have other non-hydrocarbon component like the carbon dioxide. We have nitrogen. It is different than the other type of natural non-acetic gas from different field. Okay, so this was Salt Lake, and this is from Cliffside, USA. So this is different composition. For example, in this there is no butane in the Salt Lake, USA field. There is no butane or pentane and C5 plus. When I say C5 plus, it means pentane and the heavier components. Okay, just to know, there is no olefins. Natural gas coming out of the reservoir contain no olefin. Also, the crude oil coming out from the reservoir contain no olefin. It is paraffins. For the crude oil, it is paraffin, aromatics, and naphthens only. There is maybe some isoparaffins, but no olefins are found in the crude oil, and no olefins are found in the natural gas coming out of the reservoir. And petrochemical industry actually is based on olefin and aromatics. Okay. So for the associated gas, we will find that the percent of methane is lower, 62%, and heavier components, higher percent of heavier components such as ethane, propane, butane, and pentane plus. Also, you can find carbon dioxide, hydrogen sulfide. So, as a general rule, so the composition of natural gas is not constant. It is different from one field to another, and also it's different if it is associated gas associated with the production of crude oil. So you will expect to have high molecular weight component, and if it is non-associated gas, so it's only natural gas present, it will have a higher lighter component, higher composition of the composition of lighter components will be higher, such as methane. There is also other non-hydrocarbon components, just like H2S, the hydrogen sulfide, and carbon dioxide. We have nitrogen, helium. Sometimes we have mercury, which is not welcomed at all in the natural gas, and all heavier, as I told you, heavier components. So actually, the natural gas has to meet certain standards to be pumped. Because if you want to pump this natural gas, it has to be cleaned. You don't want your pipeline to be damaged due to corrosion and pitting, hydrates, and so you don't want this hydrocarbon to damage your pipelines, and also non-hydrocarbon component to damage your pipeline due to corrosion and pitting. Also, for the calorific value, you want to adjust the natural gas to be only mainly methane, because the calorific value, the nitrogen and carbon dioxide have no calorific value, is zero calorific value. So, so for the natural gas cleaning option, we have first to once you produce your natural gas, you have to separate it from water. So using gravity. Okay. Then there is acid gas removal. You have dehydration, removal of water, mercury removal, and nitrogen rejection, which is nitrogen removal, a natural gas liquid recovery, fractionation, and sweetening. We will go like in fast way, step by step in the process of natural gas cleaning. So the first thing is to remove the water. So if the gas is associated gas, so you have oil, water, and gases. So this is a three-phase separator. You separate the water, you separate oil and the gas from the top. If it is non-associated gas, so there will be no oil, and this will be two-phase separator, only water and gas from the top. The next step after you remove the water from the natural gas using the gravity, the difference in the gravity, is to remove acid gas. In general, acid gas, what we mean by acid gas, it's H2S and carbon dioxide. And in this case, we call this gas sour gas. So the natural gas will, in the case, if it has acid gas, it will be called sour gas. Once you remove this acid gas, the natural gas will be sweet gas. So actually, why do you want to separate the H2S? Actually, because H2S mainly cause corrosion. So acid gas will react will cause degradation of your pipeline, and you don't want to damage your pipeline. So this is the main reason to you don't want. Also H2S contains sulfur. This sulfur will So if the natural gas enters the refinery plant or the petrochemical plant containing H2S, it will damage your catalyst. Okay, so you don't want to have H2S in your natural gas. Okay. Sulfur also react with if you burn this natural gas containing H2S, you will get SO2. So SO2, the emission of SO2 will give you acid rains. Okay, so this is one also of the reason why you want to remove H2S. CO2 also is not welcomed at all in the natural gas. So why do you guess we want to remove this CO2 from the natural gas? So actually, CO2 also will cause corrosion. CO2 has zero calorific value, so so it has no cost. It will actually it will reduce the selling price of your natural gas because the selling price of your natural gas depend on the calorific value of this natural gas. Also, CO2 cause corrosion. So CO2 will react with water, okay, and will cause corrosion to your pipelines and for refinery and petrochemical plant equipments. So how this acid gas is removed? There is three known process that can be used to remove this acid gas: physical absorption, physical adsorption, and chemical absorption. Okay, so actually absorption is where the gas is dissolved inside the liquid that you have or the solvent that you have. Physical adsorption, so in this case it will be just in the top, so you are using solid material and the gas will be on the top. Okay, and we'll see how. So for acid gas treatment, in this case, there is no chemical reaction, physical absorption. Physical absorption. There is no chemical reaction. Okay? And we have, in this case, the solvent will be dimethyl ether of polyethylene glycol. This is one of the process or the solvent that is used as a physical absorption. No chemical reaction occur between the acid gas and the solvent. So if you go in a fast way to illustrate this flow sheet, actually if you are using solvent, you have at least two towers. One is for the absorber, okay, the other for regeneration. You want to regenerate this solvent. So the absorber tower and the regeneration tower, and in between there is other serving facilities. So if you have your sour gas introduced from the bottom of this tower, so this tower is the absorber, okay, where the solvent extract all the sour gases from the natural gas. So you are injecting sour gas, you are getting from the top sweet gas without H2S, without CO2. From the top here, of course, if you are cleaning your sour gas, you are, of course, using solvent here if it is physical absorption. So you are using solvent, the solvent is introduced from the top and is flowing in contact with the sour gas introduced. So the sour gas will be cleaned and the solvent will be, in this case, rich solvent containing H2S and other and H2S and CO2. Okay. The gas, to be short, the rich solvent will be introduced to the regeneration tower. In this case, the regeneration would be heating the solvent. So once you can heat the solvent or introduce air, okay, or gas to heat the solvent or to separate the unwanted gases from the solvent. So you introduce the rich solvent to the regeneration tower, and you get from the top is the off gases, which is H2S and CO2 gases, and air or other gases injected. And from the bottom is the lean solvent, which means that the solvent contain no acid gases in. So here from the bottom is the rich solvent, and this is cooled and then injected to to the absorber for another cycle. Okay. So this is the main concept in any solvent extraction. If I'm saying physical absorption, chemical absorption, whatever the absorption or the way you are using, or whatever the solvent you are using, you have two towers: absorber and regeneration. And of course, to do regeneration, you have to heat this solvent to separate, or if there is a bond between, if there is a chemical bond, in this case, there is no chemical bond. But for chemical absorption, you have to break the bond between the solvent and the acid gas, and you have to heat this before regeneration. So physical, in the case, for physical absorption, in this case, we are using a molecular sieve or zeolite. So it is, or maybe activated carbon. So it is porous material, contain pores inside. You can, yeah. So this is the, in the photo here is the molecular sieve. Okay. So here in the circle here, this is a molecular sieve. It contain pores inside. Okay. The pores have a throat. It's like any rock in the, so it actually zeolite, there is natural material. So zeolite, sometimes there is a synthetic zeolite, and actually zeolite also can be natural material. Okay, depending on the type of the zeolite. So the molecular sieve here, or the zeolite, contain pores. These pores have a certain throat. Okay, so this throat allow a molecule of certain size only to pass through, and the other molecules are bigger than the size of this throat, so it cannot enter this pore. So as the gas passes through, you have gas, and this gas contain H2S and CO2. H2S and CO2 is a smaller size molecule compared to methane. So CO2 and H2S will go inside these pores, and the methane will not be able to go inside and will pass without being captured with this molecular sieve. You introduce hot air so as to remove after for the regeneration, because you want to get the CO2 and H2S outside. After certain time, there will be no capturing, because the pores are filled with H2S and CO2. No other spaces are free for capturing H2S and CO2. So you have to stop the process and do a regeneration cycle. The regeneration cycle has to, using hot air, or steam, you heat up this molecular sieve, and then the air will replace the place of the CO2 and H2S. So the third process is the chemical absorption. Okay, in this case, and it is the normal used case actually. It's used in many uh, gas reservoirs, or for surface facilities, for natural gas. So in this case, you have to remove CO2 and H2S using solvent. This solvent use amine based on, like monoethanolamine, diethanolamine, diisopropanolamine, diglycolamine. Okay, so it is actually based on amine solution. So this amine solution undergo chemical reaction. So as you can see here, so the amine here react with H2S and form sulfide, and for the CO2 it form carbonates. So this bond is easy to break. So it is, for the choice of your solvent, it has to be used, so it carry on reaction with the CO2 and H2S. But this bond, or this reaction, or the bond between the sulfur and the amine could be easy break, so as we can regenerate the solvent again and use it again. We don't want to waste your solvent, because if the reaction is permanent, as we will see in the NaOH. So if you are using caustic soda in NaOH, the reaction will be permanent. So you have to use each time fresh solvent. Okay, so will not be economic. So when you choose your solvent, you have to choose a solvent that can be easily regenerated and used back again in the process. So this is the process of chemical absorption. As I told you, there will be two tower, the yellow tower here, or the orange tower here. We have absorber and regeneration. Okay, so for the absorber here, we have the acid gas feed from the bottom of the tower. So normally the gas is feed from the bottom, because it will naturally, according to the difference in the gravity, it will naturally go outside, raise to the top of the tower, and the solvent is introduced from the top. So the lean solvent, which is mean solvent without any acid gas contained in, okay, so or acid gas free solvent will be introduced from the top. So this solvent will flow naturally because it is liquid. Will flow naturally to the bottom of the absorber tower, and we get from the bottom rich solvent. So the solvent will extract any acid gas from the sour gas, and we have sour gas produced from the top, and the rich solvent containing H2S produced from the bottom. Because we want this process to be economic, and we don't every time we don't have to use a fresh solvent, so we have to go and like conduct regeneration of the solvent. So how we will regenerate the solvent? So we will heat up the solvent and also introduce steam to the tower for also for heating. At the end, you will break the bond. You will have acid gas coming out from the top, and the fresh solvent coming. So it is here from the reboiler, so coming back as a fresh solvent introduced back to the absorber. Okay. So this is a chemical absorption. There is other solvent other else than amine, like the alkali carbonates, like for potassium carbonate, for example. Also, it can react with CO2 and H2S, and you can find this solvent in ammonia production plants because you want to remove CO2 from the syngas or from hydrogen. So you in most ammonia plants or in some many ammonia plants use potassium carbonates to remove CO2. Caustic soda or NaOH also react with CO2 and H2S could be used, but it is a permanent reaction. And the carbonate and sulfide of the sodium is permanent, non-reversible, so it is not easily regenerated. So you are wasting the NaOH, and it is not recommended to use. So now we have our natural gas free from acid gas. The next step is to conduct dehydration, which means that the dehydration we have to remove the water from your natural gas. Okay, so why we would like to remove the water from natural gas? Didn't we have just to remove it here? No, because this water is just only we use the gravitational force to separate the water from gas. So in this case, we want to reach a part per million concentration of water, which is not achievable by this way of separation. So we conduct dehydration. The dehydration is water actually. If we are pumping our natural gas, and this natural gas contain water under high pressure, and in the presence of water will form a gas hydrate. As you can see here, this is the gas hydrate as an example of what can have what is the shape of the gas hydrate. This gas hydrate can cause pitting corrosion because it's like ice balls, so it will cause pitting in your pipeline, and it is not, and also will cause corrosion, normal corrosion, erosion, and pitting corrosion in your pipeline, and also you don't want this to happen in your pipeline. So we have absorption and adsorption process. So for the absorption, so you are using chemical absorption, chemical reaction, you are using solvent. In this case, the solvent will be some glycol, ethylene glycol, diethylene glycol, triethylene glycol. So it is in the glycol family. Okay. So this glycol has high affinity to water. It will extract water or capture water from the natural gas, and then it is separated using the different boiling point between the glycol and water. Okay, the water boils at 100 degrees, the glycol boils at 104. So there is a difference in the boiling range between glycol and water. So for this flow sheet, so this is a flow sheet of extraction of water from the natural gas using glycol. So again, for the solvent extraction, so we have two towers, absorption tower and regeneration tower. So the absorption tower, where the wet gas, in this case, with the wet gas, contain water. So the wet gas introduced from the bottom, and then after meeting with the glycol, the glycol will extract the water from this natural gas, and we have dry gas. The introduced glycol will be lean in this in the top, and then after extraction of water, it will be rich glycol. Then introduced to the regeneration tower. It is heated because we said that it is different. We are using the different boiling point between the glycol and water. So because the water boiling point is 100 degrees Celsius, so you would expect the water to be coming from the top, okay, water vapor from the top, and the glycol will be liquid coming from the bottom, and then the glycol will be the fresh glycol or the lean glycol will be introduced back for another cycle of absorption. Okay, sometimes inject methanol in the gas pipeline to reduce the hydrate, to lower the hydrate formation temperature. Okay. For absorption, in this case, we adsorption we are using solid molecular sieve. The molecular sieve, the molecule of water is enough to fit inside the pores of this molecular sieve, like here in this case. So the molecular sieve contain pores. So if we see the size of the methane is larger size, N2O2 smaller size, H2O smaller size. So H2O can go inside the throat of the molecular sieve and being captured inside with the CO2 also and the H2S, and the methane cannot go inside the molecular sieve, and it will go from the top of the tower or in from the bottom of the tower, whatever the way you are injecting the gas. So back again here. So this is the flow sheet of adsorption of using molecular sieve. So we can extract water from the gas. So you can see here that there is two towers, extraction towers. They work alternatively. So once one is filled with H2O or water, so this will be closed and the other one will be used. So one in the regeneration phase, the other are in the absorption phase. Okay, so let's follow the blue line here. So we have the wet gas introduced to molecular sieve. Okay, so H2 it is introduced from the top in this case. The H2S are captured inside the molecular sieve, and the dry gas are coming from the bottom. So so after it is filled and H2, no more H2O can go inside the molecular sieve. The molecular sieve pores are filled with water. It will be closed, and we will like start the regeneration step. In this case, it is the red line. So let's see. We take some dry gas here. It is heated. Okay. Then introduced to the molecular sieve or the absorption tower, and it will come water and dry gas from the top. So you have to separate the water in this tower, and the dry gas is compressed, and maybe I'm sorry, it will be injected again with the wet gas. Okay. The other step here, after we separate the gas from the water, after we separate the acid gas removal, after dehydration, we dried our gas, we have to remove the mercury if the concentration of mercury is high. We can do mercury removal using molecular sieve or activated carbon. So it is to actually mercury cause corrosion to the brazed aluminum heat exchanger, which is not actually can cause environmental and safety hazard. It's not allowed. Mercury also cause catalyst poisoning, so mercury is not welcomed as a material in or a component in the natural gas. Two steps can be used to remove the mercury: the non-regenerative mercury sorption or the regenerative mercury absorption. So the non-regenerative, you expect that it will be damaged. So you cannot, you are using material that will be damaged. No, it cannot be regenerated again. Okay, so the regenerative mercury, you use molecular sieve, which can be regenerated back using hot gas. Okay, so this is, I will not go in more detail using mercury for mercury removal, but you have to know that the mercury is can be removed using two methods: non-regenerative mercury sorbent. The sorbent will be damaged forever. The surface of the sorbent cannot be regenerated back, cannot be used again. Like the permanent reaction of NaOH with if I cannot compare, but yeah, you can imagine that. So the NaOH conduct permanent reaction with H2S and CO2. So you have to use fresh solvent every time. In this case, also you have to use fresh solvent every time, which is costly. For the regenerative mercury absorption, in this case, you can regenerate this back again. For the next step here, after we remove the mercury, we have to clean this natural gas. From the nitrogen. If you contain nitrogen, nitrogen actually has zero calorific value. Again, it will reduce the calorific value of if you have a huge amount of nitrogen, or the composition of nitrogen in your natural gas is high, it will reduce the calorific value of your methane or your natural gas, so it will affect the selling price of this natural gas. Also, natural gas, if you the nitrogen, if it's contained in the natural gas, at the end you can have NOx, which is actually not environmental friendly and cause affect the ozone layer. So we have to separate nitrogen. Nitrogen can be separated using two-way cryogenic process and a pressure swing adsorption. Cryogenic process actually is using the difference in the boiling point between the methane and nitrogen. So if you see here, so we have methane. The boiling point is minus 161. In the nitrogen, it is minus 195. So using very low temperature and using high pressure, we will find that the methane will be liquefied and the nitrogen will be in the gas phase. So you can separate the nitrogen from the methane using cryogenic process. Okay, cryogenic separation. In the pressure swing absorption, it's like the molecular sieve one. You will end up having nitrogen, so the molecular sieve will have nitrogen inside, captured inside the pores of this molecular sieve, and the methane is not captured. Okay, so according to this, the methane can be separated, or the nitrogen can be separated from methane. This is about nitrogen removal. So, okay, again, the process that you are going, maybe if the natural gas that you have doesn't have nitrogen inside, so you don't have to do the nitrogen removal step. Okay, so the steps that is used, or the natural gas cleaning options are according to the composition of the natural gas. If the natural gas contains no mercury, so you don't have to remove mercury, or use this step. Okay, the next step is to separate the methane from the other natural gas liquid. Okay, so methane is what when we say natural gas. So the normal natural gas in the stove, used in the stove, or in for maybe for your cooking, or your in the furnace in the industry. When you say natural gas, you mean methane. So you have to separate the methane from the other gases. It is important. The other gases is important for the petrochemical industry. So ethane, propane, butane, methane is important gases for the petrochemical industry. So you have to separate methane. Actually, methane itself is important also for the petrochemical industry. You from methane it can be converted to syngas and to methanol and formaldehyde and so on. So for the you have in this step you have to separate it's called demethanizer. So you have to separate the methane from the natural gas liquid. So how we can separate this methane from the natural gas liquid? using the absorption method or the cryogenic expander process. Okay, so this is the step how we so use cryogenic separation. So what you have if you have a gas under pressure, and then you allow this pressure to this gas to expand without losing heat to the surrounding. Okay, this is called cryogenic expansion. Okay, what you will end up that the temperature of this gas will be reduced. This principle are used in this or it's called adiabatic expansion. Okay, we use this process to reduce the temperature of the natural gas. Once you reduce the temperature of the natural gas liquid will be in the liquid state, and the methane will be in the gas phase. So we can separate them from each other. Here is the, at the back expansion, what I told here is a thermal isolation wall. So this is a wall. The gas is under pressure. Once you allow this gas to expand without losing temperature to the surrounding, the gas will go cryogenic cooling. So this will allow us to reach very, very low temperature, so like minus 150 or minus 180. In this case, the ethane propane will be in the liquid, cooled in the liquid state, and the methane will be in the gas state. Of course, we don't want to have water in this case. If you have water with the natural gas, it will form hydrates. We don't want this hydrate in this process. So for this, the flow sheet illustrates the cryogenic expansion. So you have your gases here. It is the first step of cooling, heat exchanger. So you cool this gas using a heat exchanger. So it's not very so not a cryogenic cooling, because it is very cryogenic cooling will be in the minus region. So the first step is to cool this natural gas. Then using because of this cooling down, the natural gas is introduced to a tower. If there is liquid, maybe C5 plus will be condensated and from the natural gas, or separated out as a liquid from the natural gas, and is separated from the bottom, and then the gas will go to the top, from will be produced from the top of the tower. Then it will enter expander using Joule Thomson valve. So the gas is under pressure and then is allowed to expand. Once it is expanded, so it will lose the temperature. Once it is, will use this losing in temperature, or this reduction in temperature will give us to the minus region, cryogenic region, and then the separator. This gas enter a separator will be the liquid. Here in this case, the liquid will be ethane, propane, and butane, and from the top will be methane. Okay, and maybe some natural gas liquid with the methane. We expect from this process to have a purity from 90 to 95 percent. The other process is the absorption method. In this absorption method, we use oil. Okay, the oil will have a high affinity to natural gas liquid, and then it will be separated to natural gas liquid. So let's see what's happening here in the flow sheet. So we have the gas, rich gas containing methane and natural gas liquid introduced to the tower. From the top here, we have oil. The oil is better to be cooled. So at not a high temperature, a low temperature, very low temperature. The oil is introduced in this tower, and extract the natural gas liquids from the methane, and it will be rich oil. The rich oil enter a tower will be the propane, is separated from the rest of the liquid, natural gas liquid, and then another tower with the C5 and natural gas liquid also are separated from the oil. Okay. The oil are pumped back to to the absorption tower, so it is can go another cycle. From the top of the absorption tower, we have the natural gas, which is mainly methane, with a slightly small amount of natural gas liquid. also process membrane separation. You can also separate methane from the natural gas liquid using membrane. This membrane separation technology can also be used. It is used actually in Egypt to separate the acid gas such as CO2 from the natural gas. And I didn't discuss it in the acid gas separation, but it's actually membrane separation is one of the methods that can be used to remove acid gas and also can be used to remove methane from the natural gas liquid. After you separate the methane from the natural gas liquid, you compress this methane and transport it globally. So it has to be liquefied, okay, liquefied natural gas (LNG). So it is methane compressed and cooled at very low temperature and at high pressure, and transported using trucks and ships especially equipped for liquefied natural gas transportation. And okay, so you have separated. We separated the methane. We have natural gas liquid together, which is ethane, propane, butane, C4, okay, and pentane. We have to separate this from each other. It is not each one of these are variable for the petrochemical industry, but combined it is not valuable. So you have to separate this fraction or natural gas liquid from each other using fractionation process here. So so the first step, so the gas here, according to the flow. Let's say discuss the flow sheet directly, and this is the discussion of the flow sheet. But actually, the gas here is introduced, which contain methane, propane, butane, and pentane plus. So it means C5 and higher component, which has this gas is methane free, doesn't contain any methane. So from the first tower, fractionation tower, ethane is which is called the de-ethanizer. The ethane is separated from the top, and the rest of the natural gas are introduced to the next fractionation tower. Then, so now the methane, the natural gas, or the liquefied natural gas are free from ethane, and then introduced to the depropanizer. The propane produced from the top, and the other components C4 and the C5 plus are produced from the bottom. Then enter another fractionation tower where the butane is separated from C5 plus. C5 plus in most cases are called the natural gasoline. Okay, so C5 plus also is important for the petrochemical industry. So natural gasoline produced from the bottom. For the C4, we have two C4. So we don't have isopropane. Okay. So the first isomer that we have, normal pentane and isopentane. So the butane mixture are introduced to butane splitter, so isobutane and normal butane. It depends actually about on the composition of iso and normal butane if you will use a butane or butane splitter. The last step for the natural gas cleaning is the sweetening. Okay, you have to clean your natural gas from mercaptan. Okay, actually, we use in this case ammonia or NaOH. Okay, so ammonia and NaOH will react with mercaptan, which is RSH. Okay, RSH is mercaptan. The caustic solution will react with mercaptan and will produce disulfides. The disulfides are insoluble. Okay? Sometimes catalyst is used, and you can use NaOH or ammonia and it is called the Merox process. Okay? If the mercaptan is a concentration of mercaptan in your natural gas is high, you have to do Merox process or mercaptan removal process. In this case, the H2 free phase, which is only contain mercaptan. So the natural gas here is introduced to the first tower, and then the caustic solution is introduced to the top of the tower, which will have solvent extraction. Okay, so and there will be reaction. So the natural NaOH will react with mercaptan and form disulfides here. So NaOH with the disulfide, and then from the top is a natural gas free from mercaptan. Okay, and then you introduce some catalyst and air. In this process, there will be regeneration of the mercaptan. I'm sorry, of the caustic solution, because you have to separate the disulfide. It is insoluble, so it will precipitate. So if a disulfide is insoluble, and if, the air here will be coming from the top also of the separator, and the free caustic solution will be bumped back to the extractor or the absorption tower. Okay. Um, uh, So again, this is a full process of natural gas that is used to clean natural gas. So the different step, actually sometimes the H2S, in most cases H2S, if a huge amount of H2S is could be found, so we can use cloud process to transform this H2S to elemental sulfur. And again, elemental sulfur can be used in many, like battery manufacturing, and electrodes, and in the petrochemical industry, for rubber production and so on. Now we have methane as a product, okay, and then ethane separately, propane separately, butane separate, and the pentane as a separate process. All these are, so the natural gas are valuable in the petrochemical industry. And in the latest lecture, we will see how, what chemicals can be produced from each of these components. Okay, why these components are variable, why, how, what is the petrochemical material based, or can be produced using this building block, or using these raw materials. The other gas source is the refinery gas. Actually, we have also from the crude oil as a source. So we have refinery gas, a source for petrochemical. We have crude oil as a source of petrochemical based material. Okay, so refinery is slightly complicated. It's not slightly; it is actually complicated. I will not go and discuss every process in this refinery, actually, but this is a schematic overview of a refinery plant, where we, at the end, if you look at the product that we have LPG, which is a gas, propane, and butane, which is valuable for the petrochemical industry. Actually, we have also ethane produced, and ethylene, propylene produced from the refinery in the catalytic cracking, which is also important for the petrochemical industry. We have I'm sorry, naphtha, okay, or the gas oil. I'm sorry, gasoline, naphtha, and or gasoline, or if you know, it's commonly, you can know this. This is a benzene you put in your car, okay, not the benzene ring. It's commonly known in Egypt benzene, okay. So the gasoline actually is an important feedstock for the petrochemical industry, because the gasoline is a source for olefins if you are using steam cracking. So yeah, the gasoline can be steam cracked to olefins, and benzene, toluene, xylene, which is an important building block for the petrochemical industry. Gas oil also can be used as a feedstock. So actually, the crude oil industry, or refinery industry, is an important industry in the petrochemical industry. Okay, so you can here find here the feedstock for the petrochemical. According to the distillation, the product here is light and methane, ethane, propane, and butane, which is all used for the petrochemical industry. Catalytic cracking also produce ethylene, propylene, butylene, which is a building block for the petrochemical industry. Cooking, which is a thermal cracking, produce ethylene, propylene, butylene. It's a byproduct. All this is byproduct. And also for the catalytic cracking, we can produce naphtha. Okay. For cooking, also naphtha is produced, which also all of these are important product, or important building block for the petrochemical industry. For the natural gas, you can have methane, ethane, propane, and butane. Okay, so actually this is a sum of what is you have in the crude oil industry, petroleum refinery industry, and refinery gas. I will not go on more details about this process, because it will be a very, very long lecture. But I will start about talking about the other sources else than natural gas and crude oil. Actually, we know that the crude oil, due to pressure and how the crude oil is formed, it is applied to high pressure. The animals and the plant, the remaining of the animal plant are have a like uh, so due to the pressure, applied pressure is buried in the on the in the earth, and due to the pressure and temperature is converted to crude oil. This crude oil migrated to the reservoir, and it is stopped in this formation due to the cap rock in this formation. This is the conventional oil field, if a conventional way of production, and this is the port where the oil could be found in the rock. Okay, but actually there is unconventional oil, which means that there is two types. So unconventional, we can say if the core itself has pores, this pores is not connected together. So or the crude oil doesn't migrate and form it kerosene, and we will see how this will be produced. So for the oil source, we have oil shale. Right, the first oil source that can be used for petrochemical industrial potential. It has a potential to be used as a petrochemical for the petrochemical industry is the oil shale. So the oil shale, in this case, it is believed that the oil does not migrate, and it is the source rock. And the form of oil is called cryogene or kerosene. Okay, so kerosene is believed to be the precursor of a crude oil. So as the kerosene, we have this is the shape of a kerosene. So if the kerosene is applied at high temperature, you have high temperature without the presence of oxygen, it will be converted to crude oil. Okay, so this cryogene is actually in exist in oil shale. Okay, so you have to produce this cryogene from the oil shale. We have to the ex situ or in situ processing. So in the ex situ, you have to mine this, like here, mine normal mining or surface mining of this kerosene type or this oil shell, and then take this shells and apply pressure and temperature, high temperature for 150 or 500 degree in the absence of oxygen, and you force this kerosene to be converted to crude oil, and then this crude oil are processed with the normal crude oil to for production of fuel or the other fraction. Okay, the other process is in situ, where you have uh, this kerosene has to be converted to crude oil. It cannot be produced or not be produced as a kerosene. Okay, you cannot produce kerosene just pump it up. No, you have to convert this kerosene in situ. Okay, this is the other method. At like the degrees 345 degrees, 370 degrees Celsius, by heating the formation. So to heat this formation, you can use electrode or thermal or electricity. Okay, so you vary electrodes and you conduct electricity to heat up the formation and force this creation to be converted to crude oil. Okay, actually, it is believed that this oil shale is the reserves for this oil shale is 3 trillion barrels. So it is about a big, huge reserve. Okay, but it is the production is very expensive, and it is still in the very early process. The other source here is the shale oil. Actually, there is a huge development in the shale oil and shale gas in USA, and actually it is make the shale gas make again a recovery of the USA in the gas market. So you can find that if you compare the gases production in the Middle East and USA, you will find the USA a competitor in the natural gas production because of the shale gas. And the natural gas production and gases itself is an important for the petrochemical industry. So the shale oil is different. It is called tight oil because it is crude oil, normal crude oil. It is in the not in the source rock. It is the reservoir actually after migration. The kerosene. It is believed that the kerosene is a precursor to crude oil, but there is some like a debate on this. Okay, so if we say that the kerosene is converted in the source rock to crude oil, and this crude oil migrated to the reservoir, production reservoir, and that this production reservoir, in the case of shale oil, is is very tight pores, not connected pores. As you can see here, it's a very small pores, not connected together, and it is hard to produce it using normal ways. So what happened is they create hydraulic fracturing of this shale oil or tight oil to produce this tight oil. So they pump water at a very high pressure using maybe sometimes it prevents use material to increase the viscosity of the water, and whatever technique they are using, and at high pressure they fracture the shale formation so the oil can naturally flow because they created artificial paths for this oil to produce. To prevent this fracture from collapsing again, they use probant to fill this shale, these cracks. So this actually okay, harder to produce than conventional oil method, but it is actually easier than the oil shale type or the kerosene type. There is a increase in production for this type of shale oil. It is a normal crude oil. Okay, it's normal crude oil. So actually, it can be refined and so on. Shale gas also, let's talk about the shale gas. So because we talked about shale oil, so it is the same as a shale gas is the same as shale oil, but instead of crude oil is present, there is a gas present. Okay, so actually it is the normal reservoir, but it is tight, not connected pores together. So this gas cannot normally flow, else you create fracturing. Okay. Um, the oil source will continue. We talked about the crude oil, so briefly about crude oil shale and shale oil. Different. We talked about the oil shale as a potential source, but it is in the future. Shale oil as an actually way of producing oil, actually happening in the USA. Tar sand is mainly in Canada, and sometimes in the some to some extent in the USA. So tar sand actually it is type of crude oil, but it is very heavy. The crude oil contain gases, contain methane, ethane, propane, butane, and like pentane, hexane, heptane, and so on. So the material about a vast majority of boiling range. But one of this is the bitumen, the very heavy, which has a boiling point higher than 350 degrees. The tar sand is mainly bitumen, which have a higher boiling point of 350 degrees Celsius. Okay, so you have yeah, it is it has a very high pour point. So in the normal temperature that you have, it will be solid. So you can to produce this, you have to heat it up to reduce the boil point of this heavy material. Okay, so it can normally flow. So as you can see here, so the process of either in situ or ex situ. So for the in situ process, they inject steam to heat up this formation of tar sand, and then so once this is heated, the boil point of this tar sand is reduced, so it can flow at ambient condition, 350, 35 degree or 60 degree. It cannot be actually without heating. It will be solid. Okay, so once you heat it, it can flow, so you can produce it, and it is used actually in Canada. The other process is to mine it or execute to mine it and then heat it up elsewhere. As you can see here, so it is the gravity, the API. Actually, for the crude oil, when we talk about how this crude, if it is light crude oil or heavy crude oil, we will compare according to the API. Okay, so it's a way of specific gravity conversion between API and specific gravity or density. So actually, this bitumen is 6 API, which means that it's very heavy. component, and the boil point is 10 degrees Celsius, which means that at 10 degrees Celsius, this bitumen will be solid, okay, will not flow. Um, so we finished the crude oil sources or fuel sources. Now we will go back to the gas sources. We have gas hydrate. Actually, gas hydrate is a way is a source of methane. You can find this gas hydrate found in the the border or the margin of continental. So here margin, the margin here we found gas hydrate. Actually, also in cold area like Siberia. So gas hydrate actually is a six molecule of water. It's believed that we six molecule of water have a methane gas molecule caged in it. So you have it is surrounded methane molecule, as you can see here, caged with six molecules of water. Because this is found at high temperature, high pressure, and very low temperature, it forms hydrate with water, and once you reduce the pressure of this reservoir, the water will melt and the methane will be released. Actually, this is a big source, a huge source of methane from this gas hydrate, but the production actually is not high from this type. We can say that. So if we compare the composition of the gas hydrate cannot be only methane, it can be propane hydrates and pentane hydrates, but it's a normal known is the methane hydrates. Actually, it contains some other component. As you can see from this table, we have different gas hydrate deposits, and we have the composition of each. So methane, ethane, propane, butane, normal butane, isobutane, normal butane, C5 plus CO2, and nitrogen. And we can see there is a difference in the composition according to the place of production of this hydrate. Some hydrate is 99% methane, and other can be as low as 29% of methane, and other ethane, propane, and butane. So also some of these have CO2 and nitrogen inside. Okay. So the other type is the cool bed methane. So gas hydrate was a source of methane, which is methane and ethane and propane, all important gases for or building block for the petrochemical industry. Coal bed methane, from the name, it contains mainly methane and with a slightly small amount of higher molecular weight like the ethane and the propane butane type, but it is mainly methane. It contains impurities with it, oxygen and sulfur compound. It contains water also as well. So you can see that this is the coal bed. Cool bed methane, as I told you, this is a way to produce. It's produced actually. Yes, it's produced actually using fracturing and the other technique where you can. So you inject a horizontal drilling and then horizontal drilling. Hold on. Okay, so it's using horizontal drilling and then you use fracturing, okay, to facilitate the production of methane from this coal pit. The coal itself actually is important raw material for the petrochemical industry and for energy production also. So actually, it's of huge reserve in North America, in Europe, and China, and it's expected the reserves of coal is expected to continue after the running out of crude oil and natural gas. After the crude oil and natural gas are used up, the coal is expected to have to continue. Okay, so actually the type of coal, there is different type of coal actually. According to the temperature, it's like cooking. So it is so this is the early step of coal after cooking, and it will be converted to lignite coal, then bituminous coal, and anthracite coal. The different composition here is the different in the carbon content and the hydrogen content according to the type of the crude oil. So actually, we have this table comparing the crude oil composition of carbon, hydrogen, sulfur, nitrogen, and oxygen component in the crude oil and in the different type of coal. So this is the pet coal, which is the early, the very, it's not valuable. It has a very low heat content type of coal. We can see that the carbon, so the carbon content is very low, with high oxygen content, some nitrogen and some sulfur. Okay, and hydrogen is not very high, but it's in the okay, the reasonable region, yani, actually. So then lignite, which has a higher amount of carbon and a lower amount of oxygen. Okay, then we have the bituminous coal. So this is after aging for a high for and cooking it for a longer time. It has a higher actually a higher heating value. Okay, or heat content. And then the most highest grade of coal is anthracite, which has the highest amount of carbon and medium amount of hydrogen and small amount of oxygen. Okay, so this is the coal. Actually, coal is can be converted um, uh, to three phases: gas, liquid, and solid, which is called coal carbonization. Coal carbonization can convert to coal, which is like cooking the coal, heating up the coal at a very high temperature and with absence of oxygen, okay, or air. This will convert the coal to coke. Coke actually is very important solid material for the iron production and for battery production or and so on. Okay. The other byproducts that we have using the coal carbonization is gases, which is actually mainly methane, but with a very bad smell, because you expect to have sulfur in. A coal tar, which is a liquid type, a very viscous liquid type, and can be used in shampoo and like anti-dandruff, photograph and dyeing, and they have a very high, many uses. Okay, coal gases is actually methane, as I told you, so it can be used as a methane source for gas, methane gas. Coal gasification, which is one of the important steps in the petrochemical industry, and actually it is being used in China because China doesn't have a high reserve, doesn't actually have any reserve of gases, very very low reserves of gases, and it has a very huge amount of coal in China. So they are trying to use technologies like coal to oil and I'm sorry, methane to olefins, MTL, methanol to olefins, and also use coal to olefins, which means converting of coal to syngas and syngas to olefin. So this is called the coal gasification. So we have here, you can react to carbon reacting with water, which is called the gasification with the steam. You will have coal syngas and hydrogen. Okay, I'm sorry. So you have carbon monoxide and the hydrogen. We mean by syngas is a combination of carbon monoxide and the hydrogen. The other way is to use steam and the carbon dioxide to produce hydrogen. So you can use a coal as a source to produce hydrogen also. But actually the composition of hydrogen in coal is very, very small, as you can see from the figure we showed, compared to the amount of hydrogen that can be produced from methane. So for methane C, 1C compared to 4H. In the coal, it will be like a very, very low amount of hydrogen. So it is not a source of hydrogen, it is a source of syngas. So it is CO and hydrogen. So coal gasification, you can, after gasification of coal using different reactions actually, um, um, you can convert the syngas to methane, so you can produce methane from the syngas. You can produce olefins actually from the syngas using as a known Fischer-Tropsch process, and it is used in South Africa, and in and different locations. If you know the GTL, gas to liquid technology, so the gas to liquid technology is based on syngas production. So syngas can be produced from methane, can be produced from any fuel, and can be produced from coal. So gas to liquid technology is also important in the petrochemical industry because they can produce olefin products from this way. The last two gas sources that we are going to talk about is biogas and pressurized gases. So for the biogases here, it's actually the biodegradation, anaerobic degradation of the biodegradable materials, organic component, or the sewage and any waste, biological waste, based waste. So the main product in this, as you can see here from here, you can use different sources actually to convert this wastes to biogas. The biogas, if you see, is different from one source to another. So source one is waste from domestic home. Or source two is the sludge from wastewater treatment, and source three is agriculture waste. So if we see the composition of this biogas, it is mainly methane, as you can, from 50 to 60% here, from 60 to 75 percent of methane. It has CO2, it has H2S inside. So okay, so it has CO2, it has nitrogen, it has water, it has hydrogen sulfide, and sometimes it has ammonia. Okay. Biogas actually is a source of methane, as you can see. It can be used as a green natural gas or renewable natural gas. Actually, although methane it by itself is a way is a damaging to our environment because methane is the effect of methane or leaking of methane to the atmosphere is in the range of 26 times the effect of a molecule of CO2. So the effect of methane, one molecule of methane escaping to the atmosphere is 26 times the effect of one mole of one molecule of CO2. So actually, in the global warming. But in the case for biogas, biogas is a renewable natural gas, which is mainly methane. So pressurized gases. Actually, the geothermal energy is starting to getting more attention. We are saying the these reservoirs contain 3 kilometers to 7.5 kilometers down inside, containing like a very huge amount of heat. These fluids inside can contain natural gases and other gases dissolved in this fluid, and it can be used as by itself as a gas from the production of the gases dissolved in this fluid, or can be used for heating or as a heating source or for the generation of steam. It is getting potential attention now. I don't know if you see that the Americans are closing the petroleum engineering specialty and the and I think the geological specialty and converting to more non-conventional sources of underground reservoir. One of these is the geothermal reservoirs. Okay, so at the end, we can say that there is a vast majority of gases that can be gas sources and oil sources that can be used as a potential for petrochemical industry, which is non-conventional ways. On the also the conventional ways can be used for the petrochemical industry and for refinery also. If one of these sources are used up, there is other sources, and I don't expect this petrochemical industry to vanish in the very like in the near future. It will last for a very good amount of time. Okay, so thank you. Hope that you enjoyed this lecture, and I hope that I make things simpler for you. Okay,
Thank
thank
you,
you.
Dr. Rehab El-Maghraby, for a very informative webinar. I'm sure the audience benefited greatly from it. We will be sure to send the audience's questions your way as soon as possible. Thank you, attendees, for tuning in from all around the world. Please stay safe, wear a mask, and have a great day.